All right, I'm recording now. It's November 16th. Got Brandon online. We're gonna be going in and out, Brandon. Sorry about that, man. Just hang on. Turning the screen off. Okay, this one. You're gonna walk out and run the flirt. Keep the calls on the record, but. Thank you. Yeah, we'll just pop out. Okay, y'all, we're gonna do lab 3 today. And this is gonna be due after Thanksgiving. And when we come back after Thanksgiving, we have an exam. That's the new schedule, right? We come back after Thanksgiving, that's Monday and Tuesday. We have our 3rd exam. So we don't have real lab that day. This is going to be due the week after that. So let's see if I can find these dates here. Yeah, so when we come back, that'll be November 30th. That's our exam 3. And I don't really want you to be doing your lab report when you're working for that. So then we still have class the next week because of the new schedule. And like somebody said, maybe that's the 7th. December 7th. We'll be due then. That's lab number 3. Still, that does not fit into that weird no assignments due, because then we still have school on Wednesday, but we don't meet on Wednesday. We do meet on Thursday. So Wednesday and Thursday are those days where you cannot have any assignments due or something like that. I noticed that some people said that in my updated syllabus. I said like today was the day that I take up notebooks, but that didn't get moved the way it was supposed to, because I usually do that on the last day of class. So I'll give you a grade on your notebook. So just keep holding on to those if you can. And I wanted to tell you that, you know, when that day comes, I don't want you to like rewrite your notes or anything. Just want to look at your notebook, right? So don't get stressed out about that and rewrite your notes. Do anything special. All right. Today we're going to begin to talk about something that is something that we can do in lab, but it's also a good concept to understand for the exam. So we're going to call this cardiovascular physiology. And you already know a good deal about the heart. We haven't in this class talked that much about what the heart is connected to, which is the vessels and control of vessels. Now, what have we gone over? We've kind of gone over how we have a closed circulatory system. Something like a crab has an open circulatory system. Our system is closed, and the way that I imagine it, sort of like in my brain, is that being closed means, okay, blood goes into the arterial system where there's a lot of pressure. It splits up into smaller arteries and even smaller arteries and even arterioles, and it splits up finally into capillary beds. Capillary beds are pretty small, right? This is my capillary bed, which looks pretty fake. But eventually, after you get to the capillary bed, which is like in your tissues, by your muscles, you know, and all the way down to your pinky toes, that's the capillary bed. That's where the blood is delivering oxygen in the real small capillaries. Then the blood keeps going, and then it's part of the venous system. Goes to venules, veins. This is what we mean by it being closed, right? Closed here. What we're going to go over today is sort of a way that this system compensates or responds to exercise. So we're going to look at how this works at rest versus exercise. Another way to say it is we're going to compare these cardiovascular parameters, which are things you can measure at rest and at exercise. And there's plenty of things we could measure. One thing that would be cool to measure would be like oxygen content, because that's part of this story. But we're not going to use an oxygen probe. The things we're going to measure are cardiac output, mean arterial pressure, and total peripheral resistance. Let's see, chart going around. Right. So these little definitions that we're going over here are going to be fair game on the test. So it would be good to have these in your notes. You'll probably find these in the textbook too. These are not real weird definitions. But one way to remember the definition is to understand the formula. The formula for cardiac output is heart rate times stroke volume. Right? Heart rate is easy. That's beats per minute. We've already done something on heart rate in this class, so I know y'all understand that. A stroke volume is not necessarily something that we've talked about that much. So David LeBuff, you know what that is? Stroke volume? Think it has to do with stroke? It does not have to do with like a stroke in your brain that makes you fall down and paralyzes half of your face. That's not what stroke volume is. But what stroke volume has to do, maybe this is what you were talking about, is the amount of blood that is pumped out of this left ventricle. It's sort of like a mechanic's idea of what goes through a pump. You call that the stroke volume. So the stroke volume is the amount of blood that leaves this left ventricle and goes into the aorta. What's happening at the same time, you probably already understand this, that at the same time, the same amount of blood is going from the right ventricle into the lungs. At the same time, that amount is going into the rest of the body. What is that amount? The way that I'll think about it is 80 mils of blood. It's about that, 80 mils. Kind of a normal amount. If you're a little smaller, you have a smaller heart, it's a little less. If you're bigger, you might have a bigger heart, it's a little more. 80 mils, if you're not accustomed to working with mils, that's the same thing that people would say in a hospital, 80 cc, cubic centimeters. That's the same thing as with liters, 0.08 liters. So what does that look like? Okay, we haven't really looked at our heart that much in a million heart. This is 80 mils of water. Right? So our heart is pushing that out with every beat. Phew, phew. That much is going to our lungs, that much is going to our systemic circuit. That's our stroke volume. Now, stroke volume, we can estimate that according to our size. Let's say that we are over 150 pounds, like me. Today, we're going to say your stroke volume is about 0.085 liters. 0.085. Let's say if you are less than 150, and your stroke volume is 0.070 liters. So Emily, let's say you were calculating your cardiac output. You think you would know how to do that? Ms. Martinez? Measure pulse, beats per minute. Measure stroke volume. Can I just answer for you? Yeah. Stroke volume, that is liters per beat. What's a typical heart rate? You got that in your head, Julia? Yeah. Like 70 beats per minute. Typical stroke volume, 0.08 liters per beat. Multiply this, the beats cancel out. So let's all take out our calculator. Gabby, you ready? Can you do 70 times 0.08 for me? 5.6. I'll call that liters per minute. All right, that's sort of like a typical cardiac output. That's different from just heart rate, right? Cardiac output. One way that people say that is they say the cardiac output is the work the heart does. It's how much blood is moving through the heart with every beat. About 5.6 liters per minute. But it's different for everybody, right? Because we have different sizes. We all have different heart rates. So what I would like everybody in the room to do right now is to measure their cardiac output. But I would like for you to do it on a lab partner. So the last time we did this, we were taking our own pulse. Today, I want you to take someone else's pulse. Right, so you take a pulse for a minute. That is heart rate. You multiply that, you give that number to them, and then they multiply that by their stroke volume. All ready to do it? Okay, go for it. So you're sitting next to your lab partner probably. I want you to do it on your lab partner, not on yourself. We did it on ourselves last time. I want you to do it on somebody else. Got that cheat going on still? It's right here.
Oh, there we go. You have to. Okay.
I'm going with the product. Man. Okay, switch around, pick for the next person. Take this one, please.
I'm gonna beat you. I feel like I'm a bonus point.
What you got, baby? Hey, you, I said that, and you said that was fine. What you got here? Wait, it's 0.08. No, it's 0.08. Are you above her? Good. Got it? All right, everybody got their heart rate, what you still volume? You gotta know whether you're over 150, under 150. You're over, use this, under. Write that down in your notebook. That is your cardiac output at rest.
We rate ours and his.
Yeah, just keep your own. All right, most of y'all just took what is called your radial pulse. Whenever you push fingers in your radial pulse, we have a term for that. We say you just palpate. This palpation of the radial pulse. All right, but some of y'all did the carotid as well. The way to find the carotid is you kind of find your Adam's apple, which is in the front there, and then you push in there. You feel your carotid pulse there. You can either palpate your radial pulse or your carotid pulse. So, Rob did. Okay. So we're going to do something else. Another parameter that we're going to do has to do with blood pressure. We've been talking about blood pressure with the kidney. Instruments that you use to measure blood pressure is a stethoscope and a sphygmomanometer. Right? Now, I want you to have this word down for the test: stethoscope and sphygmomanometer, which would often be called the blood pressure cuff. That's okay, but I also want you to know sphygmomanometer. See, it's a meter, sphygmomanometer. That's a scientific term for the blood pressure cuff. You use a stethoscope and a sphygmomanometer to get blood pressure. So raise your hand if you've done that before. I know a bunch of pros, right? Can you be a coach? All right. Can you be a coach? All right, raise your hand over here. Pretty good. Can you be a coach? Mr. Jones, can you be a coach? Pretty good at it? Okay, you can be a coach. Alan, you a nurse? Yeah. Pretty good at it? I guess. You better or worse at doing paper airplanes? You're probably better at that. All right, I want you to understand how blood pressure cuff works. It's a part of, should be part of your notes. This might be on the test. On the blood pressure cuff, we end up listening to not our radial artery, right, but our brachial artery. That's our brachial artery right there. And this area that we're listening in, the back of our elbow, it's called our occipital region. Like this is our axillary region. This underarm, it's kind of like the underarm of our elbow. That's the occipital region. Occipital. I want you to understand what the blood pressure cuff is doing. Some of it has to do with this image right here, right? When the left ventricle contracts, pushing blood up through the aorta. That contraction of this muscle is called systole. This is that word, systole. This is going to be on the test. The systole of the left ventricle creates a systolic pressure. If this left ventricle is pushing blood up through the aorta, that systolic pressure is the highest pressure that our capillaries feel. The highest pressure that the capillaries tolerate. Now, what about the next cycle of the heart? Okay, the left ventricle contracts, then it relaxes. So Cameron, what do you think happens when it relaxes? Instead of pushing blood here, what's happening to this left ventricle when it relaxes? If you said it's being filled up with blood, you're right. Okay. When it's contracting, when it's doing systole, it pushes blood here. Then it takes a break, and when it relaxes, now this atrium is in systole, and it's being filled. Right. So a wrong way to think about this pressure is that you go from high pressure to negative pressure, right? That's not right. It doesn't go plus pressure then negative pressure. This left ventricle pushes high pressure, and then when it's relaxing, there's still pressure going through. So instead of plus and negative, it's just high and low, high and low. There's the highest pressure of the system, while the ventricle is in systole. And then there's the lowest pressure of the system. That's when the ventricle is in diastole. That's the diastolic pressure. That's the lowest pressure that the capillaries feel, but it's still positive pressure. The blood pressure cuff allows you to find the systolic pressure and the diastolic pressure. And whenever we just report blood pressure, we're given both of them. Like 120/80, kind of like average blood pressure for most folks. It's kind of odd. We're not really reporting a fraction. It looks like a fraction, right? But really what we're telling the clinician is, this is the systolic pressure. That's the highest pressure that the capillaries are feeling, and this is the diastolic pressure. It's kind of like we're saying this is the high and this is the low. Right? Now, that's useful in an ER to know the high pressure and the low pressure, but it's hard to study and take an average of that. So scientists have come up with a way to create a single number. That's called the mean arterial pressure. Mean arterial pressure. This is how you get it. Take the diastolic pressure and add that to the systolic minus the diastolic over 3. Right? You do this first, and then you add the diastolic pressure. Now, this is slightly complex, but it's not too complex for you to memorize for the exam. It would be good to memorize that. How do you calculate the mean arterial pressure. That's how you do it. All right, let's take these average numbers. This is the systolic pressure, this is the diastolic pressure. Mr. Duperson, does that make sense to you? Then you could plug those in?
Yes, sir.
Would you put 80 right here, 120 right here, and then 80 right here? Is that how you would do it? That'd be good. All right, Miss Danielle, can you start plugging these numbers in? The way you're going to do that is systolic minus diastolic first. Do that. Then you divide that by 3. Mr. LeBuff, you working on it with me? So let's do this first one right here. 120 minus 80. Do that in my head. That's 40. Divided by 3. 13.33.
Yep.
Then we add that to the diastolic. Okay. So a typical mean arterial pressure would be 93.33. Instead of talking about 120 over 80, which would be called blood pressure, here we're talking about the mean arterial pressure, which is 93.33. That'd be an average amount. All right. So here we're talking about the heart pushing blood through the aorta. The aorta is big like a shotgun barrel. It's so big, it can take a lot of pressure. Big and thick walls, but it leads to smaller arteries. Those arteries lead to arterioles. Those arterioles lead to little capillaries. So those little capillaries, they don't do well with too high of a pressure or too low of a pressure. If it's too high, you can actually pop some capillaries. If it's too low, the blood stops flowing through there. Okay. So there's another thing that plays a part here, and that's what we call total peripheral resistance. Ms. Rachel, you heard of that before? Peripheral resistance? All right. Ms. Courtney, you know what that is? Okay, this is what we call resistance. When the blood is going through capillaries, you can think of it going this way. There's sort of like some resistance that the capillaries are giving back to the blood from the wall of the capillaries, like this. It's pushing against. You know, it's like not on purpose, but it's like anytime a fluid goes through a pipe, there's always some resistance. So this pushback from capillaries against the blood that's trying to come through here is called the total peripheral resistance. And this is how you calculate it. You just put MAP over CO. It's an easy calculation. Once you get these two, cardiac output was 5.6 liters per beat. Mean arterial pressure was 93.3 millimeters of mercury. I forgot to give you the unit. That's a pressure unit, millimeters of mercury. So what would be my TPR, 93.3 over 5.6? Ms. Mackenzie Martin, you got your calculator out? Can you crank through this? 93.3 divided by 5.6. 16.6. Something like that. That would be a total peripheral resistance for these amounts of cardiac output and mean arterial pressure. But our vessels are not PVC pipes. You know what I mean, Gabby? You know how a PVC pipe is? It does not change. But our vessels are made of like living cells. You remember the names of the cells? The line. Touch that pipe. It's kind of like the cells that would be in that pipe, right? So this pipe is made of plastic, cannot break. But our capillaries can change because they're made of a type of cell that I want you to write down in your notes. It's not an epithelial cell, it's an endothelial cell. Endothelial cells line all of our capillaries. They make the capillary. They have smooth muscle around them. And our vessels, not like a PVC pipe, can either get bigger or smaller. That's what's cool. That makes us different from an android. We can compensate for stressful situations. So let's say like some kind of rougarou is chasing us. We start using up oxygen in our muscles. Our body recognizes that we are running out of oxygen. One thing that happens is the heart rate goes up. We start pushing more blood through. A while ago, I was making 5.6 liters per beat. It might go up to 8 liters per beat. Right? So, Mr. Boudreau, more blood going through the pipes. Do you think that the pressure increases? Why doesn't the pressure increase?
More volume.
Yeah. If it was PVC, the pressure would increase.
Yeah.
But it's not PVC. It is a living vessel. And just like you said, the vessel vasodilates. So that's the better word to use. It's bigger. Vasodilates. Right? If we were measuring total peripheral resistance and vasodilation occurs, vasodilation. When vasodilation occurs, total peripheral resistance, do you think it goes up or down, Aaron? Does the resistance go up or down here? Huh? Yeah. What about the other guess? You got it. Kind of remember that the resistance is this, pushing against, right? This is the resistance. So when it gets bigger, the resistance goes down. It kind of like says that that's bigger. Now it can allow more blood to go through. On the other hand, sometimes the vessel gets skinnier. Mr. Bergeron, you think the TPR, the total peripheral resistance, goes up or down in this situation? Yeah. TPR has just gone up in vasoconstriction. All right. So TPR is a way to measure the response of the vessels in these different situations. Now, one thing that can be challenging for these little vessels is, okay, high blood pressure might lead to some popping of capillaries. But what's so bad about low blood pressure? It doesn't seem like it would hurt anything. Miss Lorette, you know, what is wrong with low blood pressure? It sounds kind of healthy in some ways. What's so bad about low blood pressure? That's kind of it. Doesn't push enough oxygen. With low blood pressure, the blood's not flowing. So that happens in high school, like when you're still growing. Some of y'all still going through those growth spurts. So you have a whole lot of metabolism going on, even when you feel like you're resting. And like if you're in the hallway and you sit like this, and then you get up, and you get a little head rush. That's right there, the effect of low blood pressure. There wasn't enough pressure in your arteries to push blood up to your brain, and you almost fainted, a little head rush. That's the effect of low blood pressure. So, like you said, it's not enough oxygen to your brain or to your vessels. It's not enough blood flow to the brain. But it usually snaps back, right? But some people that are on certain medications that lowers their blood pressure, that can happen to them more usually. They can faint. They can get dizzy. Okay, so low blood pressure is not always good from vasodilation. higher blood pressure from vasoconstriction can almost be dangerous too. So some of the take home here has to do with homeostasis. And I hardly talked about homeostasis yet. But what this is all about is how our physiology tries to keep some things stable while letting other things move. What is homeostasis? One thing that it leads to is balance. Balance of physiological mechanisms. What would be a slight problem if you were talking to somebody, dean at some medical school or something, he said, how would you explain homeostasis? And you would say, keeps everything stable. Like, what's wrong with that, Miss Danielle? Does homeostasis keep everything stable?
No, it compensates, so something might not be stable, but something else is up for it.
Right. Like, what if you're being chased by something? You don't want to keep your heart rate stable.
So you have to go up in
Right.
vessels so they
Or you're
dilate.
doing exercise, your heart rate's supposed to go up. So homeostasis is still working there. This is what homeostasis is doing. You use your muscles, you start running out of oxygen. Your homeostatic mechanisms, they want to keep supplying you with oxygen, so it doesn't keep everything stable. What it does is leads to more ventilation to your diaphragm. Not stability, but ventilation. Your heart rate increases, right? But there is something that stays kind of stable, and that is your mean arterial pressure. Even when you do exercise, your mean arterial pressure tends to stay pretty stabilized by changing these two things on each side of it. During exercise, your cardiac output goes up. But what happens to TPR, Miss Erin? During exercise, you think?
Goes down.
The TPR goes down, which is another way of saying vasodilation. So by moving more blood, but having vasodilation, the effect is mean arterial pressure is stabilized. It's a pretty cool trick. It's almost like you got some kind of monitoring system that's keeping track without you having to even think about it. All right, so I'm telling you what the textbooks say, but I would like for you to see it happen. So to do that, we're going to measure blood pressures, but I want you to understand how the sphygmomanometer allows you to measure blood pressure. Let's say this is your brachial artery. Brachial artery is the one that comes down right here. Subclavian here, axillary, and then right here is brachial. All right, we're using two things at once. You're listening with the stethoscope right here at the brachial artery. All right, if you took a stethoscope and listened on your brachial artery right now with no blood pressure cuff, probably wouldn't hear anything. Blood's just going through nice and even. This is what the blood pressure cuff does. Let's say this person is sitting at 120 over 80 millimeters of mercury as their blood pressure. The blood pressure cuff impinges on this and stops it up. All right, so the blood pressure cuff pushes down, pushes up, and it closes off this brachial artery. Now, when you're listening, still nothing, right? There's no blood going through here. You don't hear a sound. How did you make this blood pressure cuff pinch off your brachial artery? Was you pumped it, pumped it, pumped it, If you're at 120, you pump it to about 140, and that means it closes off. Right now, your brachial artery is closed off. The way that this blood pressure cuff works is then you can let out a little bit of pressure, just a little bit. Let it out, and it goes from 140 to 135. Any sound? No sound. 130. Any sound? No sound. Can't hear nothing. Then you get to 126. And when you get to 126, what has happened is now you let out enough pressure to now a little blood's getting through. And you can hear that with the stethoscope. Right? What you're hearing is called the Korotkoff sounds. It's named after a person. The Korotkoff sounds. That's the sound of blood going through the brachial artery when the sphygmomanometer is on there. It's a sphygmomanometer that is impinging on the brachial artery. If this wasn't here, you wouldn't hear anything. But you're hearing it because the blood is just getting through this. When you hear that sound at 126, what you have done is you just found the systolic pressure. Because you equaled the amount of pressure that was being pushed from the heart. Miss Julia, does that make sense to you?
Yes, sir.
Like when we were higher than that, it's like the sphygmomanometer is winning, right? Right when we got 126, now it's even with the pressure of the heart that pushes through. And we keep letting the air out. Okay, what happens when we get to 120? Now it's impinging a little less, but you're still hearing. You're still hearing Korotkoff sounds. You get down to 115, 100, 9, 80, you're still hearing. Get to 77 maybe, and now all of a sudden this blood pressure cuff has let out so much air, so much pressure, that now it's not pushing on your brachial artery at all. And this sound, Korotkoff sound, it goes away because it's totally smooth. There's no friction here. And so you hear then nothing. And when you hear nothing, you have just found your diastolic pressure. You found the low amount of pressure that was sitting in this artery. So that is a way to find your systolic pressure in millimeters of mercury and your diastolic pressure in millimeters of mercury. Then you can take that number, those two numbers, and you can put them into this calculation that we just did. That is diastolic plus systolic minus diastolic, so over 3. You can get your MAP. Mr. Allen, can we practice in front of everybody? That's a yes? All right, so this is yours. You got a stethoscope you can use? Now, I'm going to do it on me. So I'm going to talk through it. So I don't want you to report my number when I lecture my blood pressure goes up. But I want to show everybody what to do. So what Alan's going to do is he's going to take this sphygmomanometer and he finds this spot where the arrow is and puts that sort of right over my occipital region, right? Okay. He also gets it so that he can watch this meter right here, meter on the sphygmomanometer, right? One thing that helps to know is what your old uncle taught you, and that is righty-tighty, lefty-loosey. You know what that means, Renee?
Yeah.
Right? To go tight, you go right. Righty-tighty. You got to close this in order for this to be sealed so you can pump it up. But you don't want to close it real hard because then you can't open it again. So you just close it finger tight. you pump this up to about 140 or 150, and then you slowly let it out by hitting it going left, so that you can watch this needle going slow. Like the professionals, they do it fast, but I want you to do it kind of slow. So you can watch that needle as it goes from 140 to 130 to 120, right? And while you're doing that, kind of doing two things at once. You're listening with your stethoscope right here. Now you can see some blue veins. That's not really what you're listening to. The artery is really kind of deeper down there. So sometimes it helps, sort of like your radial pulse. Which I don't think I'm saying right now. You know, sometimes you go to feel your radial pulse and you don't feel anything. You have to kind of push in. Sometimes you got to push in here. You got to push to this inside bone a little bit to here, or maybe push around. So if you don't hear anything, you got to push around. Sometimes you got to mess around with it with the earpieces on your stethoscope to hear right. Right. So where would you put the stethoscope through? We'll let you do it. We'll let you do this righty tighty. Right. Then when you let it out, we're gonna let it out slow. Okay. Another hint, whenever you let it out, is you can usually see the needle kind of tickle. That'll give you a hint of what you should be hearing. Right, so what you're listening for is that first sound, systolic, and then the lack of a sound, that's diastolic. Okay. So you're not gonna put that on Facebook or nothing, right?
I'll try this.
Okay. I would like everybody to do that on your lab partner. Okay, what we're going to do is we're going to use library voices. Because we haven't done this before. It helps not have too much sound. That's good. Whisper voices.
A little bit, a little bit.
If it's not working, we're gonna send a professional. You heard something? You heard choric cough sound? You heard the systolic and the diastolic? His was a little bit lower. So write it down in your notebook so you don't lose it, and then calculate that. That will be your MAP. So the diastolic on the bottom. Yep. It's still lower. Don't make me work like this. Don't be loud. Oh, you pro. Oh, look at it. You look really good at that.
That's the way that we change.
Did you get it? Okay, raise your hand if you need some help. Got it? Okay, we got alcohol and clean wipes on the table in case you want to clean off your ear. Get this phone. Do you got this? Just again, you got it? You got your numbers, and then did you hear on somebody else?
No, we had a lot of trouble with our. Yeah, let me
Everybody got numbers? Up?
Yes.
Give me your own one. They help if you like knock it on the table a little bit, or you like blow water through it real hard? Yeah, you did really good. Coming down. That was fun. I always had that done. Right, if you got your numbers, you can put them into this calculation here to get your own MAP. Right? And then once you have your own MAP, you can figure out your own TPR. That is MAP over CO. This is how you get the MAP. So everybody should have 3 parameters measured. Cardiac output. No, we're gonna go do exercise. But not yet. Well, everybody has to stay for a while. Yeah. I have a family like that. Yeah, that's all, that's last.
Yeah, there's 2 really old ones. I don't know.
Yeah. And then around like.
Make it work.
It hurts. It doesn't hurt. It just felt like I feel like. I'm sorry. No,
I should divide by 3. It's a single number that reflects Y'all got numbers over there? Miss Aaron, good? Yeah, I did really good on live. We're going next. Did y'all make it work?
Yeah.
We got numbers? Mr. Jones? You're next right here. Can you, Mr. Jones. Ms. Taylor, you got something? If you got something, you can write it down. Just getting mystery sounds, Sean? All you hear is me talking in the background?
I feel like I'm hearing myself breathe instead of
Yeah. All right, y'all can wipe off your stethoscope earplugs if you want a little. Got one last one coming. I'm gonna need a volunteer to hold flag today. We need a volunteer to be in charge of traffic today. Traffic. This is gonna give you the power. Right? Can you handle that?
Yeah.
Hey, don't pull Dr. Roach. All right, this is what we're doing. Everybody has sort of a partner. Y'all got a three-person group back there. I would like for everybody to put stethoscope if you have it over your shoulder. That one's not working. You set it over here. Okay, put your stethoscope over your shoulders. Right? Do we need some extra ones? Kelsey's gonna have one for her, right? There's no extra sitting around. Right? With every partner group, there's one sphygmomanometer, right? So put that in your hand. If you don't have the sphygmomanometer, you can take the Kim wipes and the alcohol. Right? So somebody's got the blood pressure cuff. Most people have a stethoscope. We got alcohol and Kim wipes. Mr. Jones, can you grab alcohol and Kim wipes? Right. We're gonna go do a little exercise. On the way there, we're gonna look at some art as well. So we're gonna walk to Talbot Hall. Raise your hand if you know Lydia Says. Yeah, we're gonna go look at an exhibit that includes Lydia and somebody else. And we're gonna have a flag out front going straight up. And Taylor's gonna be watching traffic for us. So this is the way we're gonna do that. We're all gonna meet outside by the Aquarius, outside the hall, but we're not gonna go across the street yet until I get there. And I'm gonna be locking this up, okay? If you gotta do something, go ahead and bring your book sack or something like that if you have to run, if you have some kind of appointment. Otherwise, we're gonna come back here so you can leave your notebooks and stuff here. But you need a notebook, but you don't need your whole backpack. So grab a notebook or your iPad or something. All right, so we're meeting outside the aquarium, but don't cross the street.
Yeah, I'll get it.
Taylor, you about to remind me to hit record?
Pause, we're recording.
All right, we're putting our data on a computer. You can put her over there on that orange table. Thanks a lot.
Where you want me to put this?
It goes on that shelf right behind the door. You got time? Come do it. Okay, Renee is going to take your numbers. So this is what I need you to be ready to tell. Cardiac output before, NA before, CPR before, right? Just these numbers. Don't go up there and say, this is my heart rate, right? You don't want the heart rate. You want your cardiac output that you get from the calculation. MAP you get from the calculation. CPR you get from the calculation. Raise your hand if you don't know how to calculate, and I'll come help you. See, she wants those three before at rest, and then she wants those three after.
I have mine. I
Cardiac
have both of
output,
our, I need your
MAP, and
rest,
CPR.
though. That's a clear. I have a question.
Are you all still calculating that stuff? Cameron, you got your numbers?
I have a question. I don't,
All right, so this is what I want you to do. I want you to come all the way up here and whisper them to Miss Renee.
it's like I put my 6.97, it rounds up. Is that fine? Let it round up?
Yeah.
Okay, because I don't know how to stop it. I'm trying to put mine on. 1, 2, pressure.
Just go up. We're kind of going by tables. But if you're ready, I'm ready for you. Okay, Robert Barrett's almost table is going first. Number 2,
Okay.
table number 2.
I need your rest one.
The
Before
before
Danielle's table,
CO
Emily's table, Brianne's table, and Aaron's table.
map is 90
That's Alan's table.
and then TPR is 12.60.
That's Courtney's table.
It goes to 16.7.
1, 7, 7.
You heard of voice line yet?
Okay. It rounds up.
Okay, so 100
So I like,
and then
that could have been
16.8.
the whole heart rate hard.
I mean, 6.
Okay, thank you. Okay. We need your rest and your exercise.
I haven't done the exercise yet, but this is my before.
Okay, I'll remember that this is your problem.
I'm gonna figure it out.
Okay, thank you.
Cameron, you ready? Or you not really ready? Okay, table 2 is found.
You need your cardiac output, mean arterial pressure, and total peripheral resistance for both before and after. Okay, sorry.
Anybody confused about how to calculate that? You got that?
We rest cardiac output.
5.04.
Okay,
84.67.
it rounds it up. So if you see it,
Okay, and then 16.8.
okay, and then after.
11.3.
Okay,
105.3.
okay,
And 9.32.
okay. Thank you. Okay,
Cardiac output before 5.95. And 92.3. 15.52. 12.87. 91.3. And 7.29.
Okay, table 2, y'all gave you those numbers to Mr. Renee? All right. You ready? All right, table 1, if you have your numbers ready. Mr. Renee, I'm ready for you. I'm available for help. When somebody say they don't understand.
okay. I need your rest. Cardiac
Our
output.
rest, okay, is 5.64.
Okay,
Then 94 from around. CPR is 16.7.
okay. Your exercise cardiac output.
13.75. 92.6. 6.73.
Thanks. All right, your rest cardiac output.
5.25.
Matt.
68.3. And then 13.06.
Okay, then the ones at exercise.
11.5. 90. And 7.8.
Okay, thank you. Okay, your rest numbers.
4.42,
Okay,
83.3,
okay.
18.85,
All right, all right.
Okay, then your exercise ones.
9.02,
Okay,
80, and 8.87.
8.7.
Yes.
Okay.
Okay,
All right, your rest numbers.
This coming Tuesday.
9.3.
Yep.
Okay.
Lab report number
Okay.
2.
And then 19.066.
And now
Like
somebody's gonna say, what about lab
Okay.
report number 1?
11.88.
You gonna say that?
Okay.
And then 64.
It's gonna be in the
And then
hall
5.3,
on table
87.
tomorrow at noon.
Okay.
Put them out. You can
See,
pick 'em up
the
at-
rest is 7.14.
Okay.
I'm almost got
That
pop and
rest
pop,
is
so I think like
7.6.
so they're
Okay.
gonna be in the hall
And my
tonight.
TPR is
Tomorrow, my
9.8.
phone,
Okay.
they're
And
gonna be
And my
closed, so
CO
people
after
won't see it.
Virgo was a 13.2.
okay.
Right?
Math was 90.
You
Okay.
can either pick it up
And
Wednesday or Thursday or Friday, right in this hall.
Your rest cardiac output.
My breast cardiac was 6.3,
Yeah, you can take that.
69.33,
If you have any questions about
and 10.05,
how to do that lab report,
Okay.
go over that, make an appointment with me or something.
85.33, and 6.09,
All right, all right. Looks like
and then
table 1, table 2
5.44.
have got done.
5.44,
Y'all's calculations are getting
Is this
down
your
here.
partner?
Yeah.
Okay.
80.6, and 14.82,
How's it going there?
and 11,
You played this game before?
95.33,
Or y'all don't play around with it, maybe?
and 8.66.
Right, thank you.
Before 6.8, 78.33, 11.56, and then 13.2, 86, 6.5.
Thanks.
Sorry, I got my numbers.
Oh, you're up here.
CO, 10.9,
Right, Mountain Jones table, y'all ready?
AP 97.6, and TPR 8.95.
All right, thank you. All right, you got yours? Yes. Okay, your cardiac output at rest.
At rest, 7.57.
Okay. Matt,
86
CPR.
and 11.36.
Okay, and then at exercise.
12.65. 96.67.
Okay.
And then 76 or 7.64.
All right, thank you. Okay, your rest cardiac output.
7.14,
Okay, Matt
83.33,
and CPR.
12.51,
All right, then that exercise.
12.54, 95.33, 7.60.
All right, thank you. All right, your rest cardiac output.
5.04. 93.33.
Okay,
20.50.
50.
Yeah.
Okay, and then exercise.
8.60. 107.
Like 107?
Yeah.
Okay,
And then 13.1.
okay, thank you. All right, your rest cardiac output.
5.32.
Okay,
92.67. 17.4.
all right, then exercise.
10.78. 8.82.
All right, thank you.
7.3,
7.31.
80.6,
All right,
and then 11.05. 9.9,
all right.
80.
Okay, everybody knows sort of what we did
8.08.
today. What we didn't go
All right,
over
thank
was
you.
what was the-
Hey, Earl.
Hey, how do you know?
My resting, the CO was 6.3 and 89.3 and 14.7.
Carolyn,
Then
you know what we did.
11.3,
What do you think our objective was?
89.3, and then 14.17. 6.5.
Too many things.
9.7.
That's whether a set
13.9.
of cardiovascular parameters.
16.5.
Can you finish it from that?
9.8.7. And 5.9.
To test whether a set of cardiovascular parameters.
Oh, no, okay. 7.0,
7.0, okay.
115, 16.6,
Oh, I told you to say that.
All right.
And
And the exercise ones.
11.0, 133.3, 12.6.
0.6.
Yep.
All right, thank you.
You got it. But don't write it like that. Right, Robert, how would you just slightly modify there?
That's whether a cardiovascular parameters
Probably change before or after. How would you say it?
The objective is to establish a set of cardiovascular parameters that are different before and after exercise.
All those make sense. So in conversation especially, or one way to say it is the overall objective of our experiment was to test whether a set of cardiovascular parameters before exercise is different after exercise. To do this, we had 3 smaller objectives. Like Kelsey, you got one of those in your head right now? One of the smaller objectives that's a little more specific. You got it? Say the whole thing. So to do that, we tested these 3 smaller objectives. Test whether cardiac output before exercise is different than cardiac output after exercise. That sentence is boring, but it's just, it gives the information that we need to give. Okay, so Emily, can you give it for a second objective? Thing. Test whether cardiac output before exercise is different than cardiac output after exercise. Second one is test whether mean arterial pressure before exercise is different from mean arterial pressure after exercise. Getting kind of boring, huh? Taylor, can you give us the number 3? Can you say the whole thing for me?
Yes, sir.
Total peripheral resistance.
Okay. The objective was to test whether the total peripheral resistance is different before and after exercise.
All right. So that was 1 overall and 3 little ones. The null hypothesis. Mr. Barrett, can you give us a null hypothesis for the cardiac output?
The cardiac output before exercise is not different than the cardiac output after exercise.
Yeah, that's it. I know that null hypothesis, regular hypothesis stuff, it can be a little confusing, but it might show up on the test again. You know, I'd like you to just always remember that the null hypothesis is the not different thing. No matter what you're expecting or what you predict, the null hypothesis has nothing to do with what you think is going to happen. It's just always the not different situation. Say it again.
You repeat what Tyler said?
What Tyler Rett just said? Tyler, you say it. Say it slow for Robert. It was like washing over his, he was like too close to the speakers, kind of.
Thank you. Yeah.
All you could hear was like reverb.
The null hypothesis. Oh man, I forgot. I got that much already.
There's no difference in cardiac output before and after exercise.
I like that one. Was Danielle?
Yes.
It's not different.
It depends on how you want to say it. As long as you're stating that there's no difference between the two, you have a null hypothesis.
Okay, are you imagining a set of figures, figure 1 and figure 2 and figure 3, Mr. LaBeouf?
No.
Are you imagining a set of figures for what we just did?
Like, on the graph,
Uh-huh.
yeah, I guess you could do like that.
Is it in your head like this? One of those is gonna be cardiac output, like this, right? Cardiac output in liters per minute. Right? What's the first bar gonna be? I'm gonna put it right here.
Yeah, I'll put before it.
Yeah, you could say either before or you could say at rest. So I kind of, I do one or the other. Rest, exercise. Kind of means the same thing if you say before, after. That's okay too. Okay, before, what was the size of the cardiac output before? You have a number in your head a little?
5.4.
After what happened?
Oh, 11.
Yeah, something like that. So that's a student's t-test right there. Sometimes people get all confused and they put cardiac output, MAP, and TPR on the same graph. You can't do that. We're gonna keep this separate. Only one graph has just this measurement here. You need a whole nother graph. I know this seems like trouble, but it's more clear if you just make another little graph. This one's gonna have MAP on it. Danielle, you remember the unit for MAP?
Yes, it is. I'm actually,
Yeah, millimeters of mercury. It's like pressure, right? What happened there? I'm not exactly sure. I didn't look at the numbers.
It might have gone up a little bit, but it probably should have.
So the values are probably slightly different. I don't know if it just went up or down, but this is another thing to look at with a student's t-test. Then the last one is going to be TPR, total peripheral resistance. It doesn't really have a unit. Might start at 15 or something like that. 20. Mackenzie, you have a feel for what this graph looks like? Start out high, probably goes lower. It drops down to a half. So this would be another student's t-test. So there's probably 3 students' t-tests. Now, people often get this and they find that's a significant difference. Now, what I don't want you to say about the significant difference is I don't want you to say, this is significantly different because the calculated T is higher than the given T. That's not why it's significantly different. I want you to tell me about the physiology, why this is significantly different. You know what I mean, Mr. Bato? Like, what is the physiology that led to this significant difference? Do you think? Cardiac output increased, right? It's kind of like it's in the formula almost. That's one place to start. Cardiac output increased. What does that mean? It means the heart rate increased. And it means the stroke volume increased. The heart actually stretched out a little bit. It could hold more. The heart rate increased because the body was demanding more blood. Right? One place that you could say that. If you wanted to go further, you could say probably something started with the pre-Botzinger complex. Told the brain that there wasn't enough oxygen, and it led to this happening. Led the heart to increase in the pacemaker. Right? That's some of the physiology. Just like y'all already know this. You could talk about the pacemaker. You could talk about it means the SA node started firing more. The pacemaker is the SA node. That's what leads to the heart rate. How does it know to increase? It's getting some information from the pre-Botzinger complex that we need more oxygen. Now, sometimes people do a student's t-test here, like Miss Aaron, what do you expect? I can't guarantee it, but like, what do you expect here when you do a student's t-test? Not different. So some students say, these are not different because of scientific error. That's not the answer. Right? How would you explain this, Miss Taylor? If these are not significantly different.
I'm not sure.
What I don't want you to think is that when they're not significantly different, that's a problem. That's kind of what we expect through the homeostatic mechanisms that purposely led cardiac output to go up and the total peripheral resistance to go down. These two things working together led to this, that the mean arterial pressure was mostly stabilized. That way we don't pop capillaries and we don't faint. It's like on purpose, our body kept this stable on purpose. That is almost like, that's an indicator of homeostasis working. So sometimes when there's no significant difference, that's good. It means that the experiment worked. Now, what's due on next Tuesday? iStalk. Probably one graph, although you might have some images of the pigment dispersal. I'll put that on Moodle, so you could use those for methods. But if it was me, probably the easiest way to get through this would be 3 students t-tests. It's kind of convention to test whether the control and the treatment are different. This control, you could call that intact. You could also call it a control. Those were the crabs that nothing happened to them. These crabs here, they got ablated. Gabby, you know what it means to be ablated? I keep using the word ablated, but you know how our crabs were ablated, what that meant? Cut the eye stalk off. I mean, instead of saying these crabs had eye stalks cut off, that's what we say, ablated. Right? We're going to test those. In the second half of the experiment, whether we could cause a rescue, all of these are ablated. These are ablated and these are ablated. But Kelsey Lee, you remember the difference between these and these? Okay, saline right here didn't cause much difference with these. And then what's the next one? Yeah, the eye stalk extract. Now, it looked like those went up. I can't tell how big they went up exactly. So once again, it makes sense to test whether these are different. This is a new control. This is like a treatment. Right? Kind of similar but different. And then the other day when we were together, I recommended maybe just go ahead and test these two. So once again, you could imagine not getting a difference between these intact and these ablated with extract. So Mason, how would you explain that if these were not different? What would you say about that in your discussion?
It was expected to injected the eye stalk with a neuro acting organ acting.
Right. Yeah. That is, it's an ablation rescue experiment. If this is not different, that means the rescue occurred. It means the function was like restored by grinding up the eye stalks and injecting that back into the crab. the eye stalk extract sort of acted like an eye stalk. Here you had intact eye stalks working. Here you had the juice from the eye stalks working, the extract. All right, if you're confused about this one, this is the one that's coming up more soon. You can let me know. I don't mind helping you. All right, like I said, those will be finished tomorrow. They'll be graded. They'll be in the hall at noon. If I can help you get that grade, if you need me to put it somewhere else, I'll leave them in the hallway Wednesday, Thursday, and Friday. That's it for today. We're getting out early.
I had lunch because I didn't have time to do my calculation, so I just,
Okay,
I need like 2 minutes to do that.
all right.